For centuries, humans have gazed at the night sky, captivated by the small reddish dot that drifts across the heavens. Mars, the red planet, has fueled myths, inspired science fiction, and challenged our understanding of the universe. Once imagined as a world teeming with intelligent life, later dismissed as a barren wasteland, and now reconsidered as a place that may have once supported life, Mars remains one of the greatest mysteries of our solar system. As technology advances, our exploration of Mars has evolved from simple telescopic observations to robotic landers and rovers that traverse its dusty plains. Each mission uncovers new clues, painting a picture of a planet that was once more Earth-like than we ever imagined. A world of ancient rivers, vanished lakes, and a climate that could have supported life. But what happened to Mars? Why did it transition from a potentially habitable world to the cold desert we see today? To answer these questions, scientists have followed a simple yet profound principle. To find life, follow the water. And nowhere is this pursuit more urgent than on Mars, where every drop of frozen ice could hold the key to one of humanity's most enduring questions. Are we alone in the universe? Mars. From the fiery inferno of Venus, we now journey to the cold, dusty plains of Mars. Once thought to be Earth's twin in its own way, the red planet holds tantalizing clues to ancient rivers, lakes, and perhaps even life. Let's uncover the secrets of this mysterious neighbor. Life as we know it thrives on Earth, where water is the lifeblood of ecosystems and the essential ingredient for existence. Scientists searching for life beyond our planet always start by looking for liquid water, the critical environmental requirement for all known organisms. This quest has taken us to an alien world that seems to defy the laws of physics. A place where water should not exist, but where compelling evidence suggests it once flowed abundantly. Welcome to Mars, the red planet, where a hidden history of water might hold the key to finding extraterrestrial life. On August 4, 2007, a Delta II rocket carrying NASA's Phoenix lander blasted off from Cape Canaveral, embarking on a 400 million-mile journey to Mars. As the first robotic scout mission under NASA's Mars exploration program, Phoenix was designed to explore the planet's Arctic plains and search for the building blocks of life: carbon, nitrogen, and, most crucially, water. By following these clues, Phoenix aimed to answer one of humanity's most profound questions: whether life is unique to Earth or if the universe is teeming with it. After months of travel through the void of space, Phoenix entered the Martian atmosphere on May 25, 2008. As the lander approached the surface, engineers at NASA's Jet Propulsion Laboratory, JPL, in Pasadena, California, held their breath. Successfully landing on Mars is a monumental challenge. Only a fraction of missions to the red planet have survived the perilous descent. But Phoenix prevailed, touching down in the Martian Arctic to begin its groundbreaking exploration. The primary goal of the Phoenix mission was to determine whether Mars's Arctic plains could support life, either now or in the past. While Phoenix was not equipped to detect life directly, it sought evidence of water, the single unifying factor for all life on Earth. Planetary scientist Chris McKay explained the rationale. When we look at life on Earth, we see incredible diversity. But the one thing all organisms share is the need for liquid water. It's the foundation for everything. That's why our search for life always begins by searching for water. Mars's surface today appears dry, barren, and inhospitable. But the red planet wasn't always this way. Decades of observations, starting with NASA's Mariner 9 spacecraft in 1971, revealed tantalizing clues of a wetter past. Images from Mariner 9 showed vast channels and valleys that appeared eerily similar to water-carved features on Earth. These discoveries sparked decades of debate. How could a planet with a thin, freezing atmosphere have sustained flowing water? Mars's current atmosphere presents two major challenges for water. First, the air pressure is less than 1/100th of Earth's, equivalent to being 20 miles above sea level here. A height nearly 4 times the altitude of Mount Everest. At this low pressure, water cannot remain stable as a liquid. Instead, it would boil away at temperatures as low as 50 degrees Fahrenheit, 10 degrees Celsius. Second, Mars is incredibly cold, with average temperatures ranging from -225 degrees Fahrenheit to -143 degrees Celsius at its poles, to a maximum of 70 degrees Fahrenheit to 20 degrees Celsius during the warmest days at the equator. Even if liquid water could exist briefly on the surface, it would quickly freeze solid. These conditions create a paradox. Mars's surface is both too cold and too low pressure for liquid water to exist. Yet the features observed, vast networks of valleys, channels, and gullies, strongly resemble those created by water erosion on Earth. Scientists considered alternative explanations, such as carbon dioxide, lava flows, or wind erosion. But none could account for all the observed features. The evidence suggested that water had flowed across Mars in the past, but when and under what conditions? In June 2000, images from the Mars Orbiter camera aboard the Mars Global Surveyor revealed astonishing evidence of recent water activity. These images showed gullies and alcoves on slopes in Mars's southern hemisphere, features that closely resemble those created by flowing water on Earth. The patterns, reminiscent of veins in a leaf or branching tree roots, appeared on slopes that received minimal sunlight, some of the coldest parts of the planet. Could liquid water still exist on Mars? NASA's Phoenix lander was sent to investigate this question directly. Using advanced instruments, it analyzed the Martian soil and atmosphere, searching for water and the conditions necessary for life. Early in its mission, Phoenix discovered water ice just below the surface, a major breakthrough. By scraping away the topsoil, the lander exposed bright, icy material that sublimated into vapor when exposed to the thin Martian atmosphere. This confirmed the presence of water ice and provided further evidence that Mars might once have had liquid water. Another key piece of evidence comes from a meteorite known as Allen Hills 84001, discovered in Antarctica in 1984. This 6-inch rock, weighing over 4 pounds, is one of only 34 known Martian meteorites on Earth. Dating back 4.5 billion years, it is older than any rock found on our planet. Astrobiologist Dr. David McKay of NASA's Johnson Space Center analyzed this meteorite and found microscopic globules of iron and magnesium carbonates, minerals that form in the presence of liquid water. These findings suggest that water once flowed on Mars 3.9 billion years ago, under conditions that might have supported life. Mars rovers like Spirit, Opportunity, and Curiosity have continued the search for water, sending back compelling evidence of Mars's wetter past. At Meridiani Planum, the landing site of Opportunity, the rover discovered spherical rocks nicknamed blueberries scattered across the landscape. These formations, composed of hematite, are typically formed in the presence of water, further confirming Mars's aqueous history. If water once flowed freely on Mars, could the planet have supported life? On Earth, life persists in the harshest environments. Organisms thrive in deep-sea hydrothermal vents, acidic hot springs, and even beneath Antarctic ice. The discovery of water ice and hydrated minerals on Mars raises the possibility that microbial life could exist, either as remnants of a distant past or in isolated subsurface reservoirs today. Scientists have proposed that liquid water might exist transiently on Mars's surface, perhaps during brief warming periods caused by volcanic or meteorological events. The discovery of recurring slope lineae, RSL, dark streaks that appear seasonally on Martian slopes, suggests that briny water might occasionally flow, albeit in minute quantities. Mars's watery past not only informs us about the planet's potential for life, but also provides insight into the early solar system. Understanding how Mars lost its water and transitioned to its current state could help scientists predict Earth's long-term future and guide the search for habitable planets around other stars. The possibility of water on Mars and the life it might have sustained remains one of the most exciting questions in planetary science. As missions like Mars Sample Return and the ESA's ExoMars rover prepare to delve deeper into the planet's mysteries, humanity edges closer to uncovering the truth about our enigmatic neighbor. For now, Mars continues to captivate scientists and dreamers alike. With its icy poles, ancient riverbeds, and mysterious gullies, the red planet remains a tantalizing puzzle, hinting at a time when it may have been more like Earth. Whether life ever took hold on Mars, or still clings to existence in its subsurface or clouds, remains an open question. But one thing is certain: Mars's story is far from over. As new missions set their sights on its rusty terrain, the quest to follow the water continues, offering the hope that one day we might find the answer to one of humanity's greatest mysteries. The story of Mars is one of transformation, marked by its transition from a warm, wet world to the frozen desert we see today. Central to this narrative is water, once abundant, now elusive. Evidence of Mars's watery past continues to captivate scientists, offering tantalizing clues about the planet's history and its potential to support life. At the heart of this exploration is NASA's Phoenix lander, a mission designed to dig beneath the Martian surface and uncover the secrets of water on the red planet. One of the most compelling pieces of evidence for Mars's aquatic history comes in the form of small, spherical rocks scattered across its surface, nicknamed blueberries by NASA scientists. These peculiar formations, made of hematite, closely resemble deposits found near Earth's hot springs and ancient lake beds, such as those near Yellowstone National Park and Lake Superior. Their presence on Mars's Meridiani Planum suggests that this vast plain was once saturated with water, or possibly even the site of an ancient lake. Further exploration of Mars's surface reveals even more evidence of a water-rich past. High-resolution images from the Mars Express spacecraft show geological features like Ionic Chaos, a large depression, and Aries Vallis, an outflow channel. These formations resemble ancient river systems carved by catastrophic floods. According to planetary geologist Jim Rice, these floods were on a scale unlike anything on Earth. If you took every river on Earth and put them in one spot, flowing at the same time, some of these flood channels on Mars would still be 20 to 30 times bigger. The evidence of ancient rivers, valleys, and catastrophic floods raises a fundamental question. How did Mars transition from a warm, wet planet to the cold, dry world we see today? Understanding this transformation is one of the key goals of the Phoenix mission. Scientists believe that for water to have existed on the Martian surface, the planet must have had a thicker atmosphere and higher temperatures in its past. Mars's early history suggests that these conditions did exist, but they were short-lived. Mars's smaller size played a critical role in its cooling and atmospheric loss. When the solar system formed 4.6 billion years ago, both Earth and Mars were molten balls of lava. Over time, as they cooled, Mars's smaller diameter allowed it to shed heat more rapidly than Earth. This rapid cooling stabilized liquid water on Mars's surface far earlier than on Earth, creating conditions that might have supported lakes, rivers, and even rain. The source of Mars's water likely came from comets and asteroids, which bombarded the planet in its early history. Unlike Earth, where intense heat caused water to boil away, Mars was cool enough to retain much of the water delivered by these icy bodies. By 3.9 billion years ago, Mars had a temperate climate, a thick atmosphere, and liquid water, ideal conditions for life to potentially emerge. While Mars was once warm and wet, it could not hold on to these conditions indefinitely. Scientists theorize that a combination of factors led to the loss of its water. Unlike Earth, Mars lacked a strong magnetic field to shield its atmosphere from the sun's solar wind. As Mars's core cooled and its magnetic field weakened, the solar wind stripped away much of the atmosphere. Without sufficient atmospheric pressure, water on the surface boiled away or froze, leaving behind the desolate landscape we see today. In 2003, NASA's Odyssey orbiter provided key insights into Mars's remaining water. Using a gamma-ray spectrometer, it mapped hydrogen levels in the top 3 feet of the Martian surface, revealing frozen water reservoirs near the planet's poles. These reservoirs contain enough water to cover Mars's surface with a layer 6 to 10 meters deep, if melted. Phoenix's mission was to confirm the presence of this ice and unravel the story of its formation and fate. Phoenix represented a significant leap in Martian exploration. Unlike previous missions that focused on the surface, Phoenix was equipped to dig beneath the ground and analyze subsurface ice. Its robotic arm, capable of scraping soil and delivering samples to its onboard laboratory, allowed scientists to study the composition of Martian ice and soil at unprecedented depths. The lander's thermal and evolved gas analyzer, TEGA, was a key instrument in this endeavor. TEGA's 8 tiny ovens, each the size of a pen cartridge, were designed to vaporize ice and soil samples at temperatures up to 1,800 degrees Fahrenheit. As the samples vaporized, they released gases that TEGA analyzed for traces of hydrogen, oxygen, carbon, and nitrogen, the building blocks of life. By sampling at different depths, Phoenix aimed to map the history of water on Mars and uncover clues about the planet's potential to harbor life. The evidence uncovered by Phoenix and other missions continues to deepen the mystery of Mars's water. Images from the Mars Global Surveyor showed modern-looking gullies and alcoves on slopes in the planet's southern hemisphere. These features, resembling Earth's water-carved gullies, suggest that liquid water might still occasionally flow on Mars. Some scientists hypothesize that geothermal activity beneath the surface periodically melts subsurface ice, causing brief episodes of liquid water flow. This process could also release greenhouse gases, temporarily warming the planet and creating unstable conditions conducive to water. The discovery of these gullies adds weight to the idea that Mars's core remains geologically active. Although Mars lacks plate tectonics, its residual heat might periodically cause bursts of volcanic or geothermal activity, melting ice and creating the fleeting wet spots observed on its surface. One of the most intriguing pieces of evidence for Mars's watery past comes from the Allen Hills 84001 meteorite. Discovered in Antarctica in 1984, this ancient rock dates back 4.5 billion years and contains microscopic globules of carbonate minerals. These minerals, formed in the presence of liquid water, provide direct evidence that Mars once had a wetter climate capable of supporting flowing water. Radiometric dating of the carbonate globules suggests that liquid water was present on Mars as recently as 3.9 billion years ago. If Mars once had water, could it also have supported life? On Earth, water is synonymous with life. Even in the harshest environments, acidic hot springs, deep-sea hydrothermal vents, and polar ice caps, microbial life thrives. Mars's ancient lakes and rivers might have provided a similar environment for life to emerge. The discovery of water ice and hydrated minerals on Mars raises the possibility that microbial life might still exist, hidden beneath the surface, or clinging to transient reservoirs of liquid water. The Phoenix mission marked a significant step forward in our understanding of Mars, but the Red Planet's story is far from complete. Future missions, such as NASA's Perseverance rover and the ESA's ExoMars rover, aim to build on Phoenix's findings, searching for direct evidence of life, and studying the planet's geological history in greater detail. Mars, once a warm, wet world, now stands as a frozen testament to the fragility of planetary ecosystems. By studying its past, scientists hope to better understand the processes that shape planetary climates and determine the potential for life beyond Earth. The Red Planet continues to beckon, its ancient riverbeds and frozen plains whispering stories of a time when it might have been not so different from our own world. As humanity pushes further into the cosmos, Mars remains one of the most tantalizing destinations, a place where the mysteries of water, life, and planetary evolution converge. Mars's frozen desert landscape might seem inhospitable, but its geology holds uncanny similarities to Earth's. Both planets feature volcanoes, canyons, and valleys, but Mars's resemblance to Earth doesn't end there. For planetary scientists, regions on Earth such as Antarctica's dry valleys serve as analogues to the Martian environment, offering clues to the potential for life on the Red Planet. Mars, at its warmest and wettest, would have been like Earth at its coldest and driest, explains planetary scientist Chris McKay. These comparisons guide NASA's Phoenix mission as it hunts for the building blocks of life buried in the icy soils of Mars. On Earth, McKay and his colleague Peter Smith prepare for the Phoenix mission by digging into the ice-covered soils of Antarctica. This exercise mirrors what Phoenix will do on Mars, testing instruments and techniques designed to detect evidence of life. We're analyzing soil layer by layer down to the ice, says McKay. By examining these frozen soils, they hope to connect findings on Earth to potential discoveries on Mars. In the Antarctic's sub-zero temperatures, life takes the form of extremophiles, microorganisms adapted to thrive in conditions as harsh as those on Mars. Extremophiles were first discovered in the boiling hot springs of Yellowstone National Park, but their diversity stretches far beyond heat. They thrive in supersaline environments, deep ocean vents, and even uranium-laden waters near nuclear reactors. Yet it's the microbes living in Antarctica's frozen deserts that captivate researchers like Smith. If life can survive transient amounts of liquid water here, he muses, why not on Mars? Phoenix aims to answer this question by searching for ice, organics, and evidence of past habitable conditions. Mars's polar deserts preserve evidence of its past climate in much the same way Earth's permafrost preserves ancient life forms. In Siberia, frozen mammoths have been unearthed after tens of thousands of years, offering glimpses into the distant past. On Mars, the Phoenix team hopes for a similar effect. "We're looking for micro-Martian mammoths," McKay jokes, referring to microbial evidence frozen in Martian ice for billions of years. Phoenix's instruments are uniquely equipped for this search, with the ability to detect organics, carbon-based compounds essential for life, and analyze the history and properties of Martian ice. Phoenix's robotic arm digs beneath the Martian surface to collect samples, which are then delivered to a suite of onboard instruments. Among these is the Thermal and Evolved Gas Analyzer, TIGA, which vaporizes samples at temperatures up to 1,800 degrees Fahrenheit, releasing gases for analysis. These gases are scanned for hydrogen, oxygen, carbon, and nitrogen, the elements of life. By studying soil and ice at different depths, Phoenix builds a map of Mars's water history, providing insights into how ice interacts with soil and atmosphere. While Phoenix was purpose-built to dig into Mars's icy soils, one of the most compelling discoveries of water on Mars came from an accidental breakdown. In 2007, NASA's Spirit rover uncovered evidence of past water when its malfunctioning wheel dragged through the soil, revealing an unexpected find, nearly pure silica. That was a serendipitous discovery, recalls one scientist. On Earth, high levels of silica are typically found in hot springs and fumaroles, environments teeming with microbial life. This find suggested that ancient Mars once had similar conditions, supporting the possibility of life. The discovery reignited debates about the red planet's habitability. Could Martian extremophiles have thrived in these silica-rich environments, much like their counterparts on Earth? Spirit's findings bolstered the argument that Mars had habitable zones in its past, and perhaps still does. The discovery of potential habitable zones on Mars brought renewed attention to the Allen Hills meteorite, a 4-billion-year-old rock found in Antarctica in 1984. This meteorite contains microscopic carbonate globules, which are significant because they form in the presence of liquid water. Additionally, scientists found structures resembling microbial fossils and crystals of magnetite, an iron oxide commonly associated with bacteria on Earth. Dr. David McKay, who led the team studying the meteorite, declared these findings as evidence of past life on Mars. These tiny structures are similar to fossils found on Earth, he explained. While many scientists remained skeptical, Spirit's silica discovery gave McKay's conclusions new weight. If microbes could thrive in hot springs or fumaroles on Earth, why not on Mars? The Phoenix mission, launched in 2007 and landing on Mars in May 2008, marked the culmination of NASA's 30-year quest to follow the water. The mission's goal was not just to find ice, but to determine whether Mars's icy soils could preserve organics and other signs of life. By analyzing the interaction between ice, soil, and atmosphere, Phoenix aimed to unlock the story of Mars's climatic past and its potential for habitability. Phoenix's landing site was carefully chosen based on data from NASA's Odyssey orbiter, which detected hydrogen-rich regions near Mars's poles. These regions, believed to contain vast reserves of frozen water, held the promise of revealing Mars's icy secrets. If melted, this ice could cover the planet with a layer of water 6 to 10 meters deep. Phoenix's task was to confirm that these hydrogen-rich areas were indeed made of water ice, and to study its properties in detail. Understanding Mars's icy history requires piecing together the planet's climatic evolution. Early in its history, Mars was much warmer, with a thick atmosphere that could support liquid water. Rain carved valleys and filled lakes, creating conditions similar to those on early Earth. However, as Mars cooled, it lost its magnetic field, leaving its atmosphere vulnerable to the solar wind. Over time, this stripped away much of the planet's atmosphere, lowering pressure and temperatures to levels that made liquid water impossible on the surface. Today, Mars's climate is a frozen remnant of its former self. Yet recent discoveries of gullies, wet spots, and silica deposits suggest that liquid water might still flow briefly during periods of geothermal activity. Scientists speculate that heat from Mars's interior could occasionally melt subsurface ice, creating transient flows of water. These episodes could also release greenhouse gases, temporarily warming the planet and allowing liquid water to exist on the surface. The implications of Phoenix's findings extend beyond water. If Mars has ice, organics, and energy sources, it could be considered a habitable zone. Microbial life could exist in isolated pockets, clinging to the remnants of Mars's ancient watery past. Phoenix's ability to detect organic materials and map the properties of ice brings us closer to answering one of humanity's greatest questions. Are we alone in the universe? If we find even a single microbe on Mars, McKay notes, it could mean that life is not unique to Earth, but rather a common feature of planets across the cosmos. A single Martian microbe could represent the potential for ecosystems as rich and diverse as those on Earth. Phoenix's mission marked a milestone in Mars exploration, but it is just the beginning. Future missions, such as NASA's Perseverance rover and ESA's ExoMars, will build on Phoenix's discoveries, searching for direct evidence of life and studying Mars's geological history in greater detail. These missions aim to unlock the mysteries of Mars's past and determine its potential for supporting life today. Mars continues to captivate scientists and dreamers alike. With its frozen plains, ancient riverbeds, and silica-rich soils, the red planet holds the promise of discovery, of water, of life, and of humanity's place in the universe. As Phoenix and its successors follow the water, they may uncover answers that reshape our understanding of life's potential, both on Mars and beyond. The search for life on Mars carries profound implications for humanity's understanding of its place in the universe. Even if the seed of life never grew to maturity on Mars, its presence would suggest that life is not an earthly anomaly, but a cosmic phenomenon. This prospect of life emerging wherever conditions permit is what drives NASA's Phoenix mission. It's a quest to uncover whether life existed or could still exist on the red planet. But before Phoenix could explore Mars's icy secrets, it first faced its greatest challenge: getting there safely. Mars landings are notoriously perilous, with less than half of all attempts ending successfully. On May 25, 2008, after a 9-month journey through space, the Phoenix spacecraft began its final approach to the Martian surface. Traveling at a blistering 74,000 miles per hour, the probe had to decelerate to just 5.2 miles per hour for a safe landing, a monumental task requiring split-second precision. This critical phase, known as entry, descent, and landing, EDL, unfolded in 3 distinct stages, each fraught with risk. The process began as Phoenix slammed into Mars's thin atmosphere, relying on friction to slow its descent. A heat shield absorbed the immense energy generated by this friction, reducing the spacecraft's speed by 99%, but exposing it to searing temperatures. Once the heat shield had done its job, a parachute deployed, further reducing the spacecraft's velocity to about 750 miles per hour. While this phase was similar to previous Mars missions, Phoenix had a crucial difference. It lacked the protective airbags used by earlier rovers. Instead, Phoenix relied on precision-engineered descent rockets clustered around its hull. These 12 engines fired in carefully timed pulses during the final 34 seconds of descent, gently lowering the spacecraft to the surface. Gentry Lee, the engineer responsible for ensuring Phoenix's safe landing, described the tense moments leading up to touchdown. When we hit the top of the atmosphere, the process of slowing down begins. In 6 to 7 minutes, we decelerate from tens of thousands of miles per hour to single-digit speeds for a soft landing. The parachute, radar systems, and descent engines all had to function flawlessly. Any misstep, whether a radar malfunction, engine misfire, or parachute failure, would mean disaster. As Phoenix approached the surface, mission controllers at NASA's Jet Propulsion Laboratory, JPL, anxiously monitored its progress. Did the radar see the ground properly? Did the computer interpret the information correctly? Did the engines fire as planned? These were the questions running through their minds as they awaited confirmation of a successful landing. At 7:53 p.m. Eastern Standard Time, the tension broke. Phoenix's radar detected the Martian surface, and the engines executed their final pulses. The spacecraft touched down safely on the Arctic plains of Mars, bringing an end to its perilous journey. For the Phoenix team, this moment marked the culmination of 5 years of relentless effort. With the landing complete, the real work began. Phoenix's first images of the Martian surface quickly arrived, revealing a barren yet captivating landscape. The spacecraft's primary goal was to search for evidence of water and the building blocks of life, including carbon and other organics. Its robotic arm was poised to dig into the icy soil, while onboard instruments analyzed samples for clues about Mars's past climate and habitability. This mission was a bold leap forward for Mars exploration, going beyond the surface-level observations of earlier missions. By probing beneath the planet's icy crust, Phoenix aimed to uncover the secrets of Mars's watery history and its potential for life. These discoveries would not only deepen our understanding of the Red Planet, but also offer insights into the broader question of whether life exists beyond Earth. The Phoenix mission embodies humanity's drive to explore and understand its place in the cosmos. If life, or even the conditions for life, once existed on Mars, it would fundamentally reshape our view of the universe. It would suggest that life is not a rare fluke, but a natural outcome wherever the right conditions arise. As the Phoenix spacecraft began its exploration, it carried the hopes of scientists and dreamers alike, poised to answer questions that have captivated humanity for generations. Phoenix's journey to Mars was only the beginning. Its search for life, water, and habitability continues to inspire, offering a glimpse of what lies beyond our world. With each discovery, Phoenix moves us closer to understanding whether we are alone, or if the seeds of life are scattered across the cosmos, waiting to grow. Mars remains a world of contradictions, dry yet carved by ancient rivers, frozen yet holding traces of liquid water. seemingly lifeless yet hinting at a past that may have supported life. Every mission sent to its surface has deepened the mystery, confirming that this neighboring planet was once far more dynamic than its desolate appearance suggests. But the biggest questions remain. Did Mars ever harbor life? And if it did, does it still persist beneath its surface, hidden from our view? The next generation of exploration seeks to answer these questions with unprecedented precision. NASA's Perseverance rover, currently traversing Jezero crater, is collecting rock and soil samples that may one day be returned to Earth, offering the most direct evidence yet of Mars's habitability. Meanwhile, the European Space Agency's ExoMars mission is preparing to drill beneath the surface, where traces of past or even present life might be preserved in the icy depths. But the search for life on Mars is only part of a larger vision. With plans for human missions on the horizon, Mars is no longer just a subject of scientific inquiry. It is a future destination. Space agencies and private companies alike are laying the groundwork for an eventual human presence, a step that could redefine our species' relationship with the cosmos. The first astronauts to set foot on Mars will not only be explorers, but also pioneers of an interplanetary future. Whether Mars was ever home to life, whether it still hides microbial secrets beneath its frozen crust, or whether it will one day support human colonies, one thing is certain. Our journey to understand the Red Planet is far from over. As new missions push the boundaries of discovery, Mars continues to call us forward, challenging us to unravel its secrets and, perhaps, to stake our own claim in the vastness of space. The story of Mars is still being written, and with every new discovery, we come closer to understanding not just the fate of a distant world, but also the potential for life on Mars, in the universe, and beyond. Thank you for watching. If you enjoyed the content, don't forget to like and subscribe to support me.